Partial Fractions video 6. We're actually into the integration now, and integration of case 1 examples. So to get the ball rolling, determine the antiderivative of this rational function that you see there. So first of all, we're going to resolve it into partial fractions based on what you've seen in some of the previous videos. So this one clearly is a case 1. We've got a pair of distinct linear factors on the denominator. So using methods we've seen previously, we get this all-important equation. Then we use substitutions, x equal 3, so we get 10 equals 5b, b equals 2. We use a second substitution, and x will equal -2, so we have 5 equal -5a, a equals -1. So by now this is getting fairly routine, this step. So if I want to take the antiderivative of that rational function, we are actually able to take the antiderivative of the partial fractions, which is easier to do. So using a and b in the case 1 form, and then applying the integral at the same time. I'm sure you're up to that if you've been watching all the previous videos. Just putting the partials down and sticking integrals using all the rules of integration, or some of the rules of integration we've seen before. Okay, now that first term can be written as so, because it fits another form we've looked at where the result involves natural log. Likewise here, it just makes it run smoother. So we have the integral of 1 over x plus 2 is natural log of x plus 2. So we have negative natural log of the absolute value of, or the modulus of, x plus 2, and the second one follows the same rule with x minus 3 plus c. You may wish to write the final answer with the first term as the positive term. That's an option you have. And it's seen as slightly more elegant. Alright, another example. Your mission, if you choose to accept it, is to find the antiderivative of what you see there. Now that is an improper fraction, which we saw in the first video in this series. So it's about time we looked at one of those. I said we use polynomial division, and we will. Now, setting up our polynomial division, you may wish to be really careful, like I've done, with all the places there all marked out, so we can be careful. You might be a bit better than that. It's up to you. Alright, so I've put in the first step there. Next step is to subtract. Use a factor of x. Subtract, and we get a remainder of x plus 2. So basically this has a remainder. So the answer is x cubed. The result is x cubed plus x plus this remainder you might remember from earlier polynomial division over x squared minus 1, the divisor. So that's what we're in fact devising if we go back to the main, integrating, if we go back to the main question there. So it might be helpful to split it up like that, and then like this. Okay, you don't have to put these brackets in, but just to make it more explicit. This term here, which we have to integrate, is going to be a case 1 partial fraction situation. So I could put that further down here on the right hand side. Now x plus 2 over x squared minus 1, you're thinking, where are these distinct linear factors? Well, down on the denominator, that's the difference of two squares, identity. Alright, you have to know this. You may have heard me say that to you. Alright, so that's where your distinct linear factors come from. So x squared minus 1 is x plus 1, x minus 1. You must know that identity and always be ready to use it. The difference of two squares. Okay, so we've got clearly a case 1. Okay, which we've seen a lot of times now. Setting ourselves up for the usual process now. So letting x equals 1 and then later let x equals negative 1. So we have 3 equals 2b. So b equals 3 on 2. Okay, so yeah, of course these parameters don't have to be integers. Okay, so they can be real numbers of any type, or just real numbers. And we have negative 1 plus 2 is 1. And we have negative 2a. A will equal negative 1/2. So we write that down then, because you can see there we have a over x plus 1. Alright, so this is what we'll have. So it equals negative 1 over 2 outside of x plus 1. You can see that's where using your knowledge of fractions can come in handy, because a equals negative 1/2. And since b equals 3 on 2, we get, for the second term, 3 over 2 outside of x minus 1. Let's go back to the integration task where we're really finding the antiderivative. So let's plug this in. So back over on our left hand side, we can now integrate these things. We've all fully finished setting up the integration. You're probably just itching to get that part done, especially the two terms here that I've just written down, because they're going to be easy, aren't they? And so writing in what the result from just a minute ago, which you now see, and just to make things really clear, because this is the first one of this we've had a video on, first one of this sort, we can do these things. Now that negative can go out the front, which will make this minus, and you see we can also put the 2 outside as well. So this is what we can have, and now we're ready to take the antiderivative. So we've got 1/4 x to the 4 plus 1/2 x squared minus 1/2 natural log x plus 1 plus 3 on 2 natural log x minus 1 plus c. So an interesting one to finish off. So the first one is a straightforward simple routine case 1. The second one was more complex, because we had to do some polynomial division, and also we had to apply identities like difference of two squares, and then chunk it and use other fairly basic rules of integration. But we did it.